And so we're going to start off with expected value. Expected value is a mean, but it's a specific type of mean. It's the mean averaged over the sample space. And this concept is a little bit tricky in that when we think of means or averages, synonymous terms, we think of how we calculate a mean, how we've done it our entire lives, which is add up all the values and divide by n. And that's how we found the mean back in chapter 2. And that's not incorrect. That is just one type of mean. It's a simple mean. It's a mean that gives the same weight to every value. And that's very logical in that if I were to take a classroom of students and I wanted to take the mean weight of those students, I would not give higher credence to some students over others. I would want every student's weight to count the same, so I would add up all the weights and divide by n. That'd be a simple mean. However, when we're talking about a random variable can have a probability assigned to each of those numeric outcomes, and that probability tells us how likely those values are to occur. So when I take a mean of a random variable, I want to average it over the sample space, or maybe another way to think about that is I want to weight it according to how likely all of the values are. When we do that, we don't use the term mean, we use the term expected value. Now, we'll use them interchangeably because when we talk about a mean of a random variable, I will expect you to know that because it's of a random variable that we are doing this expected value concept. And that'll make sense as we go along. I think you'll see how we're using it. So we'll kind of use them interchangeably because anytime we have a random variable, we would never take a simple mean. We would weight it based off how likely the values are. And I've said a lot of words here with that, and you may be like, okay, I hear all the words, but this isn't making sense. Let me explain it to you like this. If I were to go out and shoot 10 free throws, now I'm not a good free throw shooter. I haven't practiced it, so I'm not very good at it. If I were to go out and shoot 10 free throws, you would say I could take all of my outcomes. Remember, the outcomes would be the series of the words make, miss, make, miss, whatever, right? Take all of those, I could translate them into numbers, right? So let's say I take the random variable x and I say how many free throws I make. Now the possible values for x range from 0 through 10, all the whole numbers, because I can make 0 out of 10, I can make 1 out of 10, 2 out of 10, etc., up to 10 out of 10. Okay. I'm not a very good free throw shooter, and so it makes sense for you to say it's not as likely for me to make 8 free throws as it is 2. It's much more likely that I make 2 than 8. It's much more likely I make 1 than 7. It's much more likely I make 0 than 10. Those are not all the same weight. So if I were to do a simple mean of the values that x could take, which the values that x could take are 0 through 10, right? And I were to do a simple mean, so average 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, would add up all those numbers, divide by 11, and I would get 5. That would be the simple mean. But is that what you would expect from me? And that's this idea of an expected value. An expected value is a mean, but weighted based off a probability, based off what you expect to happen, right? You could say, yeah, if I go shoot 10 free throws, I could make 5, but if I already told you I wasn't a very good free throw shooter, you would not expect me to make 5. You'd expect me to make less. And so we have to weight the things that are more likely. We have to say it's more likely I make 0, 1, 2, 3 than the other one, so they need to get more credence. So I don't want to do a simple mean. I need to weight by the likelihood of those events. How do we do that? We do it by this formula that mu, again, because a random variable mean is going to be a population value, because we're dealing with probability, these all ideas, it's going to be the sum of all the x's times the f of x's. The f of x's, remember, are probabilities, and that's the weight. What this is going to look like is it's going to say the 2 free throws that I make get multiplied by a probability of, say, 0.2, because that's much more likely. And so it's going to get a weight of 0.2. then I go up to 9 free throws, and it's going to get multiplied by 0.001 because it's not very likely that I make 9 of my 10 free throws, and it's going to get de-weighted. Okay. We'll do an example on this shortly. Hopefully that idea makes sense. If it doesn't, you want an example, just hold tight. We'll get there in just a second. We're also going to talk about standard deviation. This formula is a little bit wonkier. I think I can help you make it make sense a little bit in that it looks similar to the formula that we had in chapter 2 for standard deviation. We did take a square root, we did sum up the differences between x and a mean, and we did square them. So it looks a little bit different. However, if you go back to chapter 2 and look at our formula for sigma, it was square root of the sum of x minus mu squared, just like it is, except it was divide by n and not multiply by f of x. You say it's a similar formula, but that doesn't make a lot of sense. Where did that come from? The dividing by n is equal weighting, and the multiplying by f of x is weighting for how likely that individual x is. And notice that's the same thing that happened up here. Kind of stuck that in on you, didn't they? And if you go back to chapter 2 and you look at your formula, you'll see mu equals sum of the x's divide by n would be our formula for a population mean. And what we've done is we've made that divide by n, which is equal weighting. It gives everybody the same weight. And now instead of dividing by n, we're going to multiply by f of x. So we're going to switch that out to make sure that things are weighted appropriately. Again, we wouldn't do this for a sample for sure. And if we wanted the simple mean, we wouldn't do it either. If we wanted just the, say the average GPA of students at TWU, that would be a population value. But I wouldn't want to weight students based off of anything. I just want everyone to count the same. That's when you can just add up and divide by n. But if I need to weight based off likelihood, like this idea of shooting free throws, and I know it's way more likely that I make 2 than I make 8, then I need to not divide by n, I need to multiply by this f of x. So that's where if you'll compare those formulas, you'll see we've replaced divide by n with f of x in both cases to say I need to do something slightly different because I need to average over the sample space, knowing that certain things are more or less likely to happen. Now, this formula is a pain to work with, so I have a different way to write it. It looks like this. This is the one that computationally is going to be easier for us. How we got there is irrelevant. It took some hand waving of some math. Don't stress about it. I'm not going to ask you to memorize either one of these formulas. They'll be provided for you. I give you this formula because I want you to go back into the other part of your notes and say, okay, I get it. I saw where that formula came from. I see what we're doing here. I don't like it, but I see it. And then when we actually calculate, though, this will be easier to calculate. So this is going to be the one we use. This is just to help you understand the concept. So that example we talked about, consider a baseball team that plays a 4-game series. Let X represent the number of games that team wins. And I put this here on an exam. I would not do this. I would not tell you this. It would just, I would expect you to figure out that X could be 0, 1, 2, 3, or 4. It's the first time you've seen this, so I'm just making sure we're all on the same page here. Those are 5 things that X could be. And the PMF is given below in this table. Lowercase x, all the different possible values, could be 0, 1, 2, 3, or 4, and f of x is given as those decimals. Now, before we do anything, I want to stop and make sure we're all on the same page. Remember, f of x is probability. So I could have said probability. I could say f of x. You need to know they are synonymous. Number 2, all those probabilities are between 0 and 1, check. If I have a negative there, it's a problem because the probability can't be negative. If I have something greater than 1, that's a problem. The probability can't be greater than 1. And if I wanted to, I could stop right now. I could add up all 5 of those values and I could confirm that the sum of those values is 1. If not, I have a problem. Okay, I could have given you only 4 of the values and not 5 and said, fill in the missing one. And you would say, oh, well, that makes sense. I know the sum of all the probabilities has to be 1, so I'm going to add up the other 4, subtract what I got from 1, and that's the missing value because I know this property from what we talked about in the first section. Now the question says, find the probability the team wins 2 of the 4 games. Lots of different questions we can ask. This right now is the point of the course where things can get slippery for people. You need to recognize that there's a lot of different probability questions I can ask, and you need to be able to translate what those words are to what I'm asking. So you've got these videos, you can rewatch them, you can go back, try to make sure you pick it up correctly. we need to understand that the first thing that can be asked is find the probability that, and I'm basically just pointing to a row in the table. It says find the probability the team wins 2 games. Notice because f of x is equal to the probability x equals 2, all you have to do is write down that number. Okay, there's nothing else that you need to do. Now, I'm going to make sure I'm in the habit of writing out my probability statements. I encourage you to do the same, especially for as we get to more complicated problems. Being comfortable with probability notation, I believe, will help you a lot. So I strongly encourage you to get in the habit of writing that out. But I'm basically just saying go look at the table. If it's a simple probability like that, the table gives you the f of x. F of x is the probability. Boom, there you go. Next question says, find the expected number of games this team wins in a 4-game series. That's a mean, it's population mean, and we have the formula. You go pull that formula. If you want to pause and work through this problem, see if you can do it yourself, great. If not, if you're like, no, I'm here for the example to figure it out, that's totally okay. We'll continue on with that now. What this means, remember, this means sum up all of the things happening after. The sub I means go do it for each value. Right? Remember the sub I in the standard deviation problem was do it for each row. Same thing here, do it for each row, each one of the possible x's, right? Here are all of our possible x's. And so what we're going to do is we're going to say take the first possible x, which is 0, and the first f of x, because it's sub I, so it's the same one. So do it for the first row. Okay, the first row is 0 and 0, or 0.0256. What we're going to do is we're going to multiply them. And then because we're going to sum, then we're going to add, do it to the next one. Then we're going to add, do it to the next one, add, do it to the next one, add, do it to the next one. So it'll look like this. We're going to take all of our x's, multiply by their probabilities, add it, x times the probability, add it, x times probability, add it, x times probability, add it, x times probability. And then you get to finish out the calculations, and you would get 2.4 wins. Notice if I were to just average these numbers right here, you would get 2. Clearly in this case, because it's more likely the team wins 3 games than 1 game, it's more likely they win 4 than 0, it makes sense that you would expect the team to win more than 2. Just looking at this table and knowing these are probabilities, you would say, yeah, I would expect them to win maybe 2 or 3, so getting 2.4 makes a lot of sense. Now, remember, as we talked about in chapter 2, 2.4 is not in the data set. That's okay. That's how means work. Means don't have to be in the data set. No worries. It can be, and if it is, cool, but it doesn't have to be. We don't round that. We just say it is what it is. Just like the average family is 2.3 kids. You can have 2.3 kids. Who cares? It's an average, okay? And then for standard deviation, same concept. Just go ahead and write down the formula. It's a little bit more complicated. The catch here, don't forget to square the mean that you found in the previous step. Don't forget to subtract it before you take the square root. Now you're just going to work through and you're going to take the first row x, square it, and then multiply. So it's not just this times this times this, etc. It's this squared times this. Okay. Add them all up first. That's what this bracket is telling you. Add them all up first, and then at the end of the problem, subtract the mean squared. So if you want to pause here and work through that, you can. If not, we'll carry on. So notice I'm squaring here, 0 squared 0, 1 squared is 1, 2 squared is 4, 3 squared 9, 4 squared 16. That's where those numbers came from. Pulled the f of x's from the table because I don't do anything to those. Bracket right here closes off right here. I'm going to add up all those together first and then subtract off 2.4 squared. So when I add up all those things inside the bracket, that's 6.27. When I square 2.4, that's 5.67. That's square root 0.96. That's 0.98 wins. Remember, standard deviation is in the same units as the mean would be. If I did not square root, what would that be? Hopefully you're saying it back to nobody in your room or somebody in your room who's looking at you funny. If you did not square root, that would be the variance. It would be 0.96 wins squared. Again, wouldn't make a lot of sense. That's why we square root and talk about standard deviation.